Hello. In a previous video, I talked about quality factors, the different types of quality factors, and the way in which they are computed in practice or in computers. And I would link the video somewhere. I think it should appear at the top right. So if you haven't seen that video, then maybe try to check it out. But then I think I'll discuss this as if it's just new, but then just discussing one of the methods that I mentioned in the previous video. And that method is the external quality factor calculation using power flow through ports. So one of the formulas I mentioned the last time was calculating the external quality factor with the kind of basic definition, which is the energy of the mode multiplied by the angular frequency of the mode, then divided by the power through the port. So as many ports as you have in the system. And then the power through the port can be calculated from your Poynting vector. So you have just an illustration here, which is for a particular surface. Then you have your Poynting vector pointing in some direction, and you have the normal of your area, which is pointing in some other direction. And the Poynting vector, so the method is commonly used this method is commonly used in numerical simulations by integrating power flow through the ports, or I mean not yeah through the plane, through the ports plane. I think that would be better description. So the power flow through the ports can be calculated from the Poynting vector, and your Poynting vector is the cross product of your electric field and your magnetic field. Oh, this is a mistake. It's supposed to come here. So H is your magnetic field without the star. The star means the complex conjugate, which I'll explain down here now. It is important to note when working with complex phasors, which is the result you get from CST Studio, that you typically take the complex conjugate of one of the vectors. So this is really important, otherwise you get incorrect results. So the way we would be calculating the energy through our ports, it's with the time average Poynting vector, considering also that we are working with phasors. So if we're not working with phasors, if we're working with the electric field itself, and with the time, not the phasor, then you would have this definition. So you'd have this definition which gives you the instantaneous Poynting vector. And then if you should integrate this over the area, then you would have the instantaneous power flow through the port. But then what we need is the average. What we need is the average power flowing through a given surface, and that's what we'd use to calculate the external quality factor. So this is giving us the half of the real part of the cross product of your electric field phasor multiplied by the conjugate, the complex conjugate of your magnetic field phasor. And this can also be the electric field phasor, the complex conjugate multiplied by the magnetic field. Now, generally, these two terms are not equal. So E cross H star is not the same as E star cross H. They are actually complex conjugates of each other. So E cross H star is equal to E star cross H, then everything conjugate. So this is also important to note. But the real parts of these two cross products are the same, so which is what is shown here. So the real part of this is the same. So the conjugation is necessary to correctly account for the phase difference, blah blah blah. You can find, okay, maybe not blah blah blah, but you can find out more information about this on Wikipedia. So the average power flow through the port plane can be calculated with this, and then we'll see that this the dot product of this and the normal is just, and the phase normal just gives the normal component of the time average and Poynting vector on that phase, so on the dA So what we would have is, if we should dot this by this, then you just have the component of s along this direction, and we'll see how we implement that in CST. So likewise, the energy is calculated as the half of the integral of this, or you could also use your magnetic, you could also use the magnetic field to calculate it. In CST Studio, it's normalized for all modes to 1 joule, but then we'll calculate it anyway just to see. So now diving into CST Studio, if I need to come back to this, then I'll come back and show it. Let's see. Now, before I proceed, there's one thing I mentioned in the last video that I was going to check, and that is in CST version 2020, you had this option to calculate the external quality factor from. So we had this lossy eigenmode and also Q factor external, and then I thought that Q factor external did what I want to show now, that is calculated the power flowing through the port planes and then divided it, so the average power flowing through the port planes, and divided the energy, the product of the angular frequency and the energy by it. But then I checked, and apparently it's not the case, so I'm not really sure what this calculates, because if you should look at the documentation, then it says, if I could pull that up, so I should go to help. Let's see what this brings. So in documentation, it says that it calculates the Q factor based on the external port losses of the eigenmode. So yeah, I don't know about that, because when I try to calculate it for this geometry, so I just have this cavity without beam pipes. If this would work, yeah. So these are really short beam pipes. This is what I have, and yeah, calculating that, you have that it just returns -1, and then you have the lossy eigenmode and quality factor calculating as is expected. So I don't know what is going on with it since it's 2020. I don't know if I perhaps investigate, I look into it and maybe I find some reason or where it actually works, then I would maybe give a video update. But yeah, for now, since it's 2020, I'm just going to leave it. Now back to the power estimation for power calculate the quality factor calculation for such and this. So I have an ordinary pillbox with 2 ports, and I'm going to calculate the power, the average power flowing through this port and the average power flowing through this port. So for that, I hope I have everything right. So I already ran the simulation for 10 eigenmodes, so I have 10 eigenmodes, and let's see, I'm going to calculate for contour. Let's see which mode I'll calculate for. Just a random mode, okay, maybe mode 4. And I'll explain why I picked mode 4, mode 4, mode 5. I'll explain why I pick it when we're done. So first thing I'll do is I'll calculate the quality, the external quality factor, using the lossy eigenmode, that's using the frequency, the real, and the, so Q factor lossy eigenmode uses the complex frequency and calculates the loss factor. So this is what we have. If I should log that, then I have this. Now for us to calculate our power, first of all, we need our Poynting. Do I have this? Where is it? Yes, we need to get our Poynting vector, but then we are not going to get this. What we instead are going to get is this, because what we have in CST is your phasor. Then we have 2D 3D field results, then go to mix 3D fields, and then a dialog opens. Oh boy. A dialog opens, and we have to specify the 3D fields that we want to calculate. So here calculating for mode 4, so I go to mode 4 E and mode 4 H, and then what I want to do here is I want to do the vector product. So type vector prod A and B. And remember, what we are calculating for is A and B conjugate, complex conjugate. Now, to get the complex conjugate of your field in CST, what we do is we do a single quotation mark. So it's, I don't know if I can make, I don't think I can expand this. So I can't expand it, but then there's a single quotation mark there. So that's the complex conjugate. I think I could also check the help here and see if it's written. Yes, it's here. So if you should click on, if you should click on help here, then this pops up, and then you can see some operators. So you see that this is a complex conjugate operator, and then you have other operators. Then the vector product that I did is here. Then you can also do a dot product, scalar multiplication. You can do so many other things. So if you just click on help, you get that. And then if you click on function list, then you get some standard functions that are defined. So for example, pi is already defined, epsilon naught, mu naught, c light, and some other things. So just to make sure everything is correct, we are doing this. So that would give us, I'll call it maybe x underlined s. So I would click on OK, and I think I could leave it as, yeah, vector product. It doesn't matter. Then if I should evaluate that, then what you get is you have under your 2D 3D results here, you have a mixed 3D results folder, and under there you have your pointing. So smart scaling, log, and I can't really see anything, but yeah, this is what you, I mean, it's, yeah, this is what you have for the pointing. So I hope I got the correct field. Yeah, 4. So that's mode 4E and mode 4H. Okay, yeah. Now something I noticed, I think I would say something. So generally for different modes or for some kind of calculations, you could actually click on set frequency, so that and then you could click on sweep so that it calculates for all your eigenmodes. So if I should click on sweep frequency, evaluate all available samples, then I click OK, this does not work. Oh wait, maybe that actually works. I tried it before, it did not. Let's see if I get an error. Yes, of course. Yeah, it does not work. So I have this error here that frequency loops are currently not supported for discrete monitors. So I haven't really looked into that to find a way to circumvent that, because then now I'm restricted to only calculating for one mode at a time. So defining the vector product for one mode and then calculating every other thing for one mode, which sucks. So yeah, you could also change it to currently displayed fields, but let me see, I think even that, once you, let's see, yes, once I mess with this a bit, once I mess with this and change it to something else, then changing it to the default, remember it was currently displayed field default, changing it to default does not correct it. So it's either you define a new vector product that's mixed 3D template, or you click on fixed frequency. I think this should work, although the frequency is set to 0, but I think this should work. Yes, this works, so no more error, and this calculates. So that's just something I noticed. And now we have a pointing vector. So we have a pointing vector. Now the next step is to use this to find the power, which is pointing this definition. I'm going to keep the half also, and then I'm going to show how, yeah, you take the real part. So what I want to do is I have this term, and then I want to use this to calculate s, but not just calculate s, but then I'll dot it to the normal vector of the surface. So I'm going to do all of that in the next step for one of the faces, then do it for the other face. Although this device, the pillbox, is it's ideally symmetric. I mean, it should be symmetric, but then we'll see that there are some discrepancies with the result. The power flow from the two ports, although they should be exactly the same. So for this, that you have this symmetry about the is it XY plane, then you could just calculate for one of the faces and then um double that, but then I would calculate for the two, and then you see that there are some slight differences, which is because of the mesh on the two faces are different, so it gives some difference in the result. For a final mesh, I would expect that the power flow from the two ports converge, but I did not check because this one for some reason took a lot of time to run. I don't know, probably it's because of the frequency range I was considering, but then the number of tetrahedrons wasn't big, but I didn't, yeah, have so much time or patience to look at why it was taking so long, so I just let it run and did some other things, and yeah, that worked for me. So now we want to calculate the power flow. So the integral of the normal component, because this only takes, I mean, would calculate the time average of S and then dot it with the normal vector, which would give the normal component, which filters at the normal component. So that's what I'll be doing. So I go to evaluate on arbitrary coordinate. So this is one way, and then I go to area or face. Now you want to change this to cylindrical coordinates. Now I didn't actually check with XY whether it considers, because I look at this as yeah, I did check, because when you take the Cartesian coordinate system, then it gives points all over the plane that you'd, whatever plane you define, and I don't know if during the integration it only considers where you have field, so the whether it takes field values outside the bound and considers that, because then that would be wrong, because you'd have a larger area. I did not check that. I just changed it to cylindrical coordinates so that I am sure that what I'm considering is just this face and not the entire plane, and not the entire plane containing the face. So I would go to cylindrical coordinates, and I want the normal to be Z, so I want this plane, and then I want this to be at this face, which was, maybe I should go to, okay, now I can't click that. I think it was LBP minus L cavity divided by 2. I think that was it. So cylindrical, and I do not want the max range. I want R min to be 0 and R max to be R cavity. I think I at this point I have to check. I have to check my parameter list. So I have R cavity, L cavity, and LBP. Not even R cavity, I need RBP. Good thing I checked. Then you have RBP, and then the F min I want it to be 0, so your azimuthal, and then the F max to be 360 degrees. Now this is in degrees. I think in some other places you use, okay, I won't say, because I can't remember exactly if you use radians or degrees, but here it's degrees. So once I'm done defining it, so first I want to calculate on 2D area of face, then change to cylindrical coordinates, and now I want to view the points on which this would be evaluated. Now I can't move this, so I would have to move this. So let's turn this off. So these are the points that would be, these are the sample points that you would get your pointing and then evaluate it as the integral. So this appropriately defines what we want. So your R from 0 to RBP, and then if I should change this to, let's say, 180, you'd see how the points also change. So if I should draw points, then you have just a semicircle. So I'll change it back to, where is that? 360 and draw points. Yes, so it's back. Now, it's already automatically selected the pointing and vector that we calculated. Now remember what I said, we want to calculate the normal. So you go to your component, the normal, and then we want the real part of the normal. So this is what we have here. So we want the real part, and then we want the normal component because of your s dot n. We want the normal component, and that's what you have. Now we want to take the integral of this. Do we have any term in front of it? No, it's just s. Do we have any term? Yeah, no, we do not have any constant. So hopefully I wrote that correctly. Now to integrate it, we have result value. So we could either select integral 2D, integral f of x 2D, or you get maximum, minimum, or any other thing. Now, if you should, this is also important. If you select integral 2D, right? If you select integral 2D, this would calculate the integral of this, which is correct. This is because we do not have any factor in front of it. If we had a factor, even if it's a constant in front of it, we would not be using this. So just to as an illustration, I will show this, the difference between calculating, yeah, I'll show it with this. Then you'll see that it's important when we are calculating the work, the energy stored in the system. So if I should click on OK, and then I calculate the integral over the surface, then I have 5.6. Cool. 5.6 E4. So this is 5.605 E4. Keep that number in mind. Now let's say I wanted to double this, right? So I could either just create another post-processing step and multiply it, or I could come to specials, and when I click on specials, I do 2 multiplied by. But then look at this is f of x, right? If I should click on this, then okay. But what we are doing here is not any function, it's just taking the field and integrating it over this face. So if I should solve this, I would get exactly the same answer, because it actually does not even see f of x. It doesn't even go into special, because one mistake I've made sometimes is I just mistakenly select integral 2D, and then I define a function here, and then when I integrate, I have exactly the same answer. So it was 5.6 E4, and then you see it's exactly the same answer. So that's because you just have to be careful to select integral f of x to the, then it sees it considers this function in specials. It considers this function. So that's if I should click OK, then this should be 10 point or 1 point something e to 6. 1.12 or something e to 6. Yeah, or e5. So the other one was e4. So that's what you have. So just some things to take note of. So, but for this integral 2D is okay. I'll just delete this just in case. Oh boy. I'll delete this because I have to share the file someday, which I don't think so. Yes, calculated for one face, then I duplicate it and then go for the other face, which would be on the other side of Z. So exactly the same settings, but then on the other side of Z would be plus L and plus L, and that's okay. Now you see what we have. I hope this is correct. Yes, L cavity over 2. So you see that we have some discrepancy. Result is 5.6, and then this is 4.47, so 4.5. So it's different on the faces, even though for this I expect that it should be the same, and I think it's because of the mesh. Now the mesh on the two faces, I'll view it I'll show you now. Let's close this and then view the mesh. Go to simulation and then view the mesh. So the mesh on the two faces is actually different, and I think this calculation is quite sensitive. You see, it's not also the best. It's not also very fine. So this is the face, and then I'm going to press a key on the keyboard and it's going to change, and you notice the difference. You see, it's I mean, it's the same mesh resolution, but then this difference apparently affects the result this way. So you see, so yeah, using this method, I think you would have to maybe refine the you have to refine the mesh on this face and then the other face, and I think generally we should do a mesh convergence study. Then this should be they should both converge to the same solution, but I will not do that. So yeah, so we have these two. So what I like to do is, and also you notice the negative, and this is because of the orientation of the normal, where when I use it I'm going to absolute everything later. So for example, if the face you defined pointed in the other direction, then you have a negative of your pointing. So but then we need the absolute value anyway. So yeah, it's the orientation of the face in CST. That's why. Now we have the power, and then I said that the energy stored in the mode is normalized to 1 joule. So this is all we need, and then we can go ahead and calculate the external Q. So we'll go to general 1D and then mix template results. Then I would select the frequency of mode 4 and then select the integral and then the other integral. So what I want is 2 pi 2 times, I'm going to use pi pi. I don't know, I think this is tiny, but then I already thought 2 pi times a. Then my frequency here is in the unit is in gigahertz, so I'd have to multiply by 1e9, then divided by the absolute of b plus, so the sum of the power through the ports, absolute, I hope I haven't made any mistake, of c. And yes, if I didn't make any mistake up until this point, then this should give the external quality factor, the correct Q. So this is 1.14 e to 5. I don't think this is, I think I made a mistake somewhere, but let's see. So mode 4 no p. So you can just so you could either go to the maximum and then move this this horizontal bar, or you could just press P on your keyboard and then press the position you want to go to, so position 4. This is 2.3, this is 2.3 E5. Okay, I think I missed something. Wait, let's see. Yes, I missed the half. Yes, I missed the half from S. So if I should go back and include that, so this would be settings. Yes, so this should be 0.5 multiplied by everything. So I missed the half. 0.5. I could have also included it in the computation of the pointing, but yeah, I missed it there, and I'll just put it here instead, and that gives okay. Calculate. Let's see. It's not supposed to take this much time. Yeah, of course, there's something wrong. I think I did not type that well. Yeah, of course, not 0.5 bracket. I missed the asterisk. Yes, so that's 2.28. Now I don't know if I can make this bigger, but then what is here is 2.28 e to 5, and then what you have from the complex frequency calculation, which is I think the real part of the I always mix this up. It's either the real part divided by the 2 multiplied by the imaginary part, or the imaginary part divided by 2 times the real part, one of those. So you see that we have 2.28 and then 2.3 e to the 5. So that's pretty close. Now let's try for another mode, and let's try for mode 6. Mode 5 is the same mode, but they're different polarization. So you see it's the same external quality factor. Let's try for mode 6, and maybe we should look at mode 6. Yeah, this is what it looks like. So dipole mode 2. So I'll just go over here and change this to mode 6 and mode 6, and also make sure to change this to mode 6, and then I can evaluate all of them at once. So what we have is 46.1, and then from the complex frequency calculation, what do we have? We have 46.08. So pretty close, results. Now you could also try for mode 7, and you'd get basically the same results. Then finally, I said that the energy was 1 joule, but then we could also do the integral, because why not? And see, so no, not mixed 3D result. Evaluate on arbitrary coordinates. So for the power, we evaluated on arbitrary coordinates, and then we evaluated on a 2D phase. But then for the energy, we want to evaluate on a 3D volume. Now, to solve this, we leave it in Cartesian, because it's not necessary. Then what we want to do is we want an integral in this case. So one thing we could do, if we should look at the formula, we could use the E field or the H field, and then basically we want this, and then the dot product of E multiplied by the complex conjugate. So we would need to write a function. Basically, would need to write a function, and so what I would select is integral f of x 3D. So, and what do I want to integrate? The absolute and then the complex part. However, wait, I think this would be a problem. Yes. So if you try to do this, then it said complex results only supported with result value 1D of plot field values. So I could not find a way to do this. Because what I would want is I want to specify E, and then I want to specify the complex conjugate. So I did not find a way to do that. I think maybe one thing I could do, first of all, let me any mode at all. Let me change this to the X component. Let's see if this works. Okay, still does not work, so it's not because it's absolute. So I could not find a way to get over this, and I can't choose another thing. Oh, I mean, I think I could choose the real part if that works. Yes, I could choose the real part and then choose the imaginary part, and then have to expand this and then calculate. But then luckily I don't have to do that, because there's a different way I could do it. So instead of specifying this, I specify the root mean square value. Now if you should look in the documentation, I hope I get it here. Yes, you see that definition of the root mean square is exactly what we want. It's half the real part of e square plus the imaginary part of e square, which is what we would get if we should evaluate this formula that we have for energy. So instead, and then what we have is the square root. So what we need is the square of this. So I'll specify the root mean square value here. Then under my specials, what I want to do is I want to do epsilon naught, that's eps 0 multiplied by x, so $x now represents the root mean square value, which is a square root of what we want. So I would have to do this square, and then that's it. If I got everything correctly, so it doesn't matter which mode, because all the modes, the value should be 1 joule. So hopefully there's no other thing I did not do, and then if I should evaluate this. Yeah, it takes some time. Oh boy. It does take some time, but it shouldn't take this long. I hope I did not make any boo-boo. Look at the messages. Let's see, 2 pi a CST, which one is this? Problem converting expression. Okay, yeah, this is done. So it wasn't this error. So you have that is 0.9979. So that's approximately one. I mean, the mesh is not the finest. So if you really want, yeah, really accurate results, then I mean, it's already one basically. So if you try for any other mode, for example, I could go to, let's say, mode 10. I have 10 modes here. I could go to mode 10. It's exactly the same thing. So if I should integrate this and wait again forever, it's going to show 1 or 1 point, usually 0.99 something or 1.0 something. This takes quite a while, and any moment now. And I'm thinking of it, I should have paused. Okay, yeah, you have 0.9975. For some modes it will be 1.01 or something. Now something you could also do, something else you could do is you could specify step size. Now when I specify this, it takes, depending on how fine I want it to be, it takes a while. The result changes a bit, but then I haven't checked to see how much it changes, if it actually gives improved results, because in the end, ultimately, when you do this, I think what happens is that the points that you do not have are interpolated. And yeah, I mean, if your result, depending on your mesh, is already not very fine, I don't really think you can improve it by taking more points. Instead, you should refine your mesh to get that. So that's one part of what I wanted to show. Now the second part, if you should observe, I skipped modes 1, 2, 3, and then I purposely skipped some modes to try to calculate the power, the external quality factor. And this is because of what I mentioned in the last video. So in the last video, I said that for modes that are strongly trapped, so strongly resonating inside the cavity, I do not really trust the external quality factor, which is calculated using any of the methods. So I haven't benchmarked this with any of the methods and experiments to see which one actually gives a really good result. But in from my experience, the quality factors of such modes are highly mesh dependent. So if your mesh changes slightly, then the quality factor gets different. And I'll show this. Now, for example, let's see for Mode 1, for example, if I wanted to calculate the quality factor with this method and compare with the frequency, the complex frequency method. So I have this, and then also remember to change this to mode frequency 1. Then if I should evaluate this, what I have is on this, please, if you know a way to calculate for all the frequencies, all the modes, the pointing for all the modes at once, please let me know. any comments, and maybe others would also benefit from it. So you have 5.1 times 10 raised to power 11, but then if you should look at the Q factor of mode 1, you have that is 7.99 e to power 10, so they are not close at all. And you would also notice the same if you should calculate for mode 2, mode 3, and mode 10, and some other modes that are strongly trapped. So what I mean by strongly trapped is you do not have the mode does not propagate into the beam pipe, or it propagates really weakly into the beam pipe, which means that the external quality factor is really high. So for very high external quality factors, it's very sensitive to the mesh resolution, and you generally do not have the same results. And not just to the mesh, but then also to many other things which I do not know. And then why do I say this is I ran another simulation. So for this simulation, I considered just 10 modes, and this gave me 69. So the same frequency range, 1.8 to 2.5 gigahertz with 69,023 mesh cells. And then I ran a different simulation, but then with 30 modes. I ran another simulation with 30 modes for which had the same number of tetrahedrons. So basically the same thing, but then I just specified a different number of modes. Then so just to see, the only thing I changed was the number of modes, and I had 30 modes. And I also did compare the results from the power flow for some modes. So for example, I think mode 13 was propagating. Let's see. Yes. So mode 13 was propagating. I won't go ahead and calculate it again. So what I obtained as the Q factor was 8.09, and then if you should look at with the lossy eigenvalue mode 13, you have that this is 8.09, so pretty much the same, or approximately the same result is what you get. However, the other modes that are trapped, like mode 1, also you do not get the same result. Now what I did was I took the result from this and compared it with this, and you could see for yourself that the modes that are propagating, you have that the external quality factors aligned, which is only these modes, and mode 13 and these other ones. For these low Q modes, also these ones I checked for mode 23 and also checked for mode 30, it corresponded with the result. But then the other ones where you have that it's high, you see that the results from the two simulations do not correspond. At least up to 10 modes, you have that the results from exactly the same simulation it does not correspond. And this is because these high Q modes are really sensitive to the mesh resolution, so you should be careful when reporting or interpreting high quality factor mode results, because at least for now I can't think of a method that I don't know which of them is correct. Oh, now something I haven't checked is if I doubt is if the results from the power flow method, if it gives the same results irrespective of the number of modes you consider. But then I doubt that it does for the same mesh. Well, it's already a lot of time, but then we could check. Let's just see this. So I'm going to take mode 1, for example. I already calculated for this, and then it was, I think, 5 point something times 10 raised to power 11. So I'm going to check for this one if it is at least, that is the external quality factor, whether it's correct or wrong, because I haven't compared with some experimental results, whether it's correct or wrong, if it is at least consistent across simulations. So I'm going to change this to mode 1, and this to mode 1. So, and then make sure to change this also to mode frequency mode 1. Yes. And I missed this. So what I'm checking now is for the same mesh, do I get exactly the same result, which would mean that at least it is consistent if you have a particular type of mesh. So it's not, so you have here it's 1.2 e raised to power 8, and then you even see that the power flow from the two ports, it's wildly different. I hope that is not a mistake on my part. I just have to confirm that that is not a mistake, because that's too different. So vector product EH prime, and then minus L LBP, yes, and then for the other one it's the same, and then integral to the yes. Yes, everything is the same. So this is something I also mentioned before that, well, I haven't mentioned it, but then for, yeah, everything is basically the same. I mean, I duplicated it. So you see that for your trap modes, you have also this very different power flowing through the ports, even though this should be symmetric and you should have exactly the same amount of power flowing through each of the ports, but then you have this much difference. So just be careful with the external quality factor calculation for irrespective of the method. If you also know any study that maybe has benchmarked the numerical simulation with some experiment, so that we know which method at least is most likely to give you the result. Now, I also did a convergence study at some point in time past of your frequency, your complex frequency method for calculating it, and if I remember correctly, it never converged. It always fluctuated. That's the external quality factor. I mean, it was always fluctuating. So yeah, I could never really get it to be stable with making the mesh finer. So I think I left it. I mean, I only did one study, so it's not like I really looked into it so much. But I haven't done it for this power method. And you see, the power method is, I mean, you have so many other steps to take. So that's it. If you have any questions, or if there's something I said that maybe it's not clear or maybe it's wrong, please leave mention it in the comment, and then we could, yeah, discuss it, or maybe others could learn from it. And yes, I did not intend for this video to be long, but then there you have it. Okay, until next time.